In this video, we're going to talk about searching. It's part of the chapter on searching and sorting algorithms, but for this video, probably long enough as it is, we're only going to talk about the search part. So searching is really important. It's important because with these data structures we've developed, in particular with the arrays and with the linked lists, we often have to search in order to be able to do anything. Okay, so that's why they're important. Now, when it comes to stacks and queues, their order or their access is limited. So we can only get to either from the front or the back. So the idea of searching doesn't really make any sense. Okay, so but for arrays and for linked lists, it certainly does. Okay, so we use the search function first of all just to determine if something is in the list or not. You know, does the array we have contain a 20? Does the linked list contain a 35? You know, does it have a certain string or a certain float value, whatever? Okay. Um, it also can be used if we're in a data structure that is sorted as it goes along. Okay. So we need to know where to place it. So if you want to maintain a linked list where everything is sorted, like the sorted linked list we did before, you have to be able to search for an item to be able to find out where to put it. Okay. And then finally, if you're going to delete an item, you have to search to find it first. Okay. So searching becomes an important task for sure. Okay. So the search algorithms we're talking about, again, we can use either for arrays or for linked lists. And it comes down to two, basically. The first idea is for any kind of data that you have, so it doesn't have to be sorted, doesn't have to be organized in a particular way. And it's called a sequential search. A sequential search is pretty straightforward. So I've got an array here that is not sorted. Okay. The sequential search says that I'm going to start my code by going to the first item in the array. Okay. Let's say I'm looking for 27. Is this what I'm looking for? It's not. Go to the next one. This one, 27. Nope. This one, nope. Not there. Now we've got it. And typically we will return the position. So this is 0, 1, 2, 3, 4. This would return 4. It's the fourth position that we found the item. Okay. If it doesn't find it, it will keep going until it reaches the end of the array or the length, or if it goes to the length as the index, because the index started at 0, then it knows it's done. So we'll denote that it didn't find it by returning a -1. It's by convention. You can do something different if you need to. Okay. So let's take a look at what this code would look like. You log in first, because apparently it logged me out while I was messing around. That's okay, because I don't think I'm sharing the screen. So let's just do all this stuff at one time. Okay. Stop the share there. Share over here. Okay. So I need to change directories. The right directory. And then I can look at the sequential search. Okay, so this is the idea again. So let's start down here that we're going to create this array. I've just got an array of 6 here. Okay. And I'm going to create a constant integer for the length of that. Okay. Let's see if I can make this a little bit smaller in case you're on your phone. This may look weird. It's not going to let me do it. Okay. It is what it is. Sorry about that if it's confusing or too small. So we've got our constant integer length equal to 6. It's in all caps because that's by convention what we do. Okay. And we want to basically ask the user, we're making this a little bit nicer. We wouldn't have to. We're going to ask the user, what do you want to search for? Okay. We're going to save that as a CH. We're then going to run the sequential search on the array, the length. Remember, when sending an array to a function, it's common, if not even more. It's almost required that you send the length along, and then the character that we're searching for. What it's going to return is the location in the array that it finds it. Okay, so that's what we're sending to our function up here. Okay, so this one, we're templating this. Note that in my function down here, I'm not When I go to call it, I don't have to, I mean, I can put in int here if I want, but it's not required. It will figure out, it will infer the type, but I don't have to rewrite the code if I send it doubles instead. And I tested that code to make sure that it does that. Okay. So we're going to use element type here as our templating, as our the variable that holds the type variable. So we're going to send it an array here. Here's our array list with the brackets. That's how we know it's an array. It's constant because we don't want search. Search should never change anything. We're going to send along the length. Okay. We wouldn't have to send along the length if we made it global, but we're not in this case. We're going to send along the length, call it length. And then we're going to have another, an item here is what we're going to call another constant is what we're sending, or sorry, what we're searching for. Okay. Again, since this is templated, we're making sure that doesn't change either. Okay. So I'm setting up my initial location as an int equal to 0. My initial found Boolean is equal to false. Okay. I'm then going to loop, and I'm looping while the location, which is what we're going to iterate through, looking for our item, starting at 0, it's less than the length. If it's greater than the length, even if it's equal to the length, we've gone too far. In our 6 items, I can go 0 through 5 legally. If I get to 6, I should be done. Okay. We also need an and here, it's not found. If we find it, we want to not go through the loop anymore. Okay. So each time through, we're going to take a look to see if the list at that position, at the LOC, starting at 0, is equal to the item. If it is, our found is equal to true. Okay. We'll come back around to the while next time, and that'll be it. Okay. And this ends the while here. That starts something else. Okay. If not, if we didn't find it on the first try, we're going to increase the location by 1 up until we hit the end. So either found becomes true at some point, or we run out of items and this first thing becomes false. The location, it becomes equal to the length. Then it's going to stop. Okay. When it stops, found will have a value. Okay. Either true or false. And the location will be the last place that it was before it stopped. Okay. So we've got an if found here. So if it found it, we're going to return that location. Okay, that's where it was. Because when the found is true, okay, this location will not get incremented. This will stop. So it'll stop where it found it. Okay. If not, it's going to return the -1, which is our marker to say that it was not found. Okay. So remember, whatever you use as your the way to tell that something is not found, it can't be anything other than the type. So it can't be a string or whatever. It's got to be an integer. That's why we use -1. Okay. So then we simply call the function here. Okay. And then if it's equal to -1, then we say that that item was not found. If it was not equal to -1, then we know it was found. And the position it's found at was the LSE, which we set LSE equal to this. It's not the same variable as it was in the function, remember, but it does have the same name. Okay. It ends up having the same value, but different memory locations. Okay. So let's take a look at this. I'm going to do the quick and dirty compiling, not give the name. Remember, you should always have an executable file. Do not use a.out like me. Okay, let's say I'm searching for 56, should be there. Found it at position 3, which is good. Run it again. I'm searching for 456, which was not found. Okay. Now, what I should have done, but didn't, because I did do some checking, but it's often simpler in these small cases to go ahead and print out your array just so you don't have to look back and forth in the code to make sure that it found what it's supposed to find at the right location. But I can look at my code, and 56 should be at 0, 1, 2, 3. So that's correct. Okay. So that's the idea of the sequential search. The negative to the sequential search. So the positive is you can always use it, no matter the data structure, no matter the organization of the data structure. The negative is it can take a really long time. Okay. Worst case scenario. So the best case scenario is that you find it immediately. You have one comparison. If you have 100 items, the worst case scenario, you'll have to do 100 comparisons to check every one to see if it exists. So the worst case scenario is if it's not found or if it's the very last item. You have all those comparisons. Okay. So that becomes the problem as the sizes uh, get bigger. Okay. So we can figure out, let's see what I want to share here. Okay. So I can share this. We can figure out the analysis here. Okay. So if we want to get the average number of comparisons, it's not going to be good, but just to figure that out. And I'm going to gloss a little bit over the math in this class, and we'll do that a couple of times. The reason being that when you take algorithms, it's typically the next course that you take, we're going to get in all the math. So we're going to just get a preview here. Okay. So to figure out the average number of comparisons for a successful search, okay, when that works, then we have to think about all the possible cases, how many comparisons there are for each case, and then add the number of comparisons and divide that by the number of cases. Okay. So if we do this, okay, the average number of comparisons, then we have, let's see, we've got here. So the first item is in the list. It'll be just one comparison. If the second, it's two, and so forth. So if we do 1 plus 2 plus 3 plus all the way up to n for all the items that we have, okay, and these are we use the numbers 1, 2, 3. We don't use what's really in those positions. Okay. You add all those together, divide that by n. That's going to give you the average number of comparisons that you have. Okay. And this is something that you may have hit in math, but if not, it's worth noting down because it comes up all the time. The sequence 1 plus 2 plus dot 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 plus n over n is equal to, we just know this. Someone's proved it. You can prove it if you want to. N times n plus 1 divided by 2. Okay. So that's the first part of what we're doing here. So that's, uh, let's see, where to talk about that. Yeah, then we have to divide it by the number of cases that we have here. So 1 over n times this is equal to n plus 1 over 2. Okay. Which means more or less half. So if you have uh, a list of 1,000,000 items, then on average, the sequential search will make 500,000 comparisons. Not very efficient. Okay. And again, you should understand that it's half. You don't have to know why for this class. Okay. So other things, other searches we can do is that we can, let me find the right, here we go. If our data is sorted, okay, so I'm going to get rid of that guy. I'm going to move up this guy. We have a list that is either sorted or we sort first. Okay. We can do what's called a binary search. Okay. And the idea behind the binary search is that we have sorted data, which tells us something. Okay. So let's keep track of our numbers for our indexes here. Just that'll help us out here. So this is at 0. This is at 1. That's at 2. That's at 3. That's at 4. That's at 5. That's at 6. At 7. We've got 8. And we've got 9. Okay. So the idea when we're searching a sorted data structure, so the idea behind binary search is we're going to start in the middle. Okay. We determine the middle. We know the length. So the length divided by 2 is roughly the middle. Okay. So in this case, if we have the 5 or 10, which is our length, divided by 2, we get 5. Okay. So that means we can start pointing at this, the 5th element here. We're going to start there. Okay. And let's say we're doing a search for 25. Okay. So I'm going to start by going to the middle at position 5. And I'm going to say, does this equal to my search term? Okay. So again, let me put here So another box here that I'm searching for 25. Okay. So is this equal to 25? So is list bracket 5 equal to 25? It's not. Okay. But 25 is less than 79. Okay. Which means I don't care. I can't get to those. I no longer care about anything to the right of this. Okay. These do not matter. It can't be there. Okay. So I'm going to change the right endpoint. Okay. So I start with a range of 0 to 9. My range is now 0 to 4. I know it's not 5. Still got that messed up. I know it's not 5. I know it can't be greater than 5 because the number is less than 79. So the range then becomes 0 to 4. Okay. I can make this here too. Okay. So the initial range, I'm going from 0 to 9. Okay. I look in the midpoint of 5. Okay. I'm then going to look, I know it's going to be on the left-hand side. I'm going to look at 0 through 4 is the range. Okay. I'm going to look in 2. In this case, we have success. Okay. So when we do that and move this to 2, we immediately find that. Okay. That's the idea of the binary search. And we keep going, okay, until we're out of items and basically the left and right are going to cross each other at some point. Okay. Or we find the item. Okay. Let's look at another example here. Actually, while we're here, if it had gone the other way. So let's say we're searching for 320, or let's do, yeah, 321. 321 is fine. We're searching for 321. Okay. Again, our initial, we start with 0 to 9. We look in 5. This time we're going to move the left. So the 9 stays the same, but we're going to move this to 6, or 1 plus the midpoint. Okay. The average here. Okay. And then depending on how you calculate the mid, you'll search either that's where that arrow went. You'll search either the 7 or the 8 and keep breaking it down from there. Okay. So with the binary search, at every search, you look in the middle of your range and then you reduce the range roughly in half. Okay. So that's basically how that's going to operate. Okay. So this code's a little more complicated. So let's take a look at the code for this one. Okay. So the setup down here is a little bit different. I still have my constant integer for length. I still have, I'm setting up the array of that size. I've got my CH for the character that they wanted to search for, location that comes back. But what I'm doing, I'm setting my initial item in my array to be 0. I'm then going through and just adding 5 every time. Okay. So I have 0, 5, 10, 15, and so forth. Okay. I'm then asking the user for a number, getting that information back, doing just like we did before. So the binary search itself has the same basic items here. Okay, it's going to have a list that we're setting as a constant. It's going to have the length, which is an integer, and it's going to have another constant for the item we're searching for. Okay. So in this case, we're going to be using the first, the last, and the mid, which is how we're going to move around among the items of the array. So the first is initially equal to 0. The last is equal to the length minus 1, be 9 in our case. So that 0 to 9 is our range. And then we have the mid we're going to calculate here. Okay. So we initially have our found equal to false, just like we did before. Okay. So our while loop here, the big thing here, we're looking for first being less than or equal to last, because at some point they're going to cross when we know we're done. Okay. When we've covered all the items, that's how we know we're done. Or if it's found, we're also going to stop. So we just calculate the mid. as first plus last divided by 2. That's going to concatenate any portion. So it's going to do it. It's like a floor function. It's going to be the lower one. Okay. And then it's going to check that mid to see if it's equal to the item. If it is, found as true. Good. Okay. If not, we have two options. If the item at the mid is greater than the item we're looking for. Okay. So we're looking for a 25. We find a 30. Okay. So that lets us know that we have to look at the left side. It can't be any further. It's already too far. Okay. So we set our last being equal to the mid minus 1. Okay. If not, then it's the case that what we're searching for is bigger than what we find. Okay. In which case, we're going to change the first. It's initially 0. We're going to move it to the mid plus 1 and keep going. Keep going until they cross when we've ran into all the elements or we find the element we're looking for. Okay. As before, if it's found, we're going to return this mid, the last mid. Again, it gets turned true when mid is equal to the item, so that's where it should be. If not, we're going to return the -1, which lets us know that it was not found. Okay. So that's the basic idea behind that code. So let me do a quick and dirty compile of this. Okay, this one needs to be a power of 5. So if I search for 35, it's going to find it, position 7. Okay. If I run it again and search for 234, it's not going to find it. Okay. So that's the basics of the binary search. It will become a question for us, especially in algorithms, if it's worth it to sort stuff, because sorting is going to be its own problem. Okay. So again, without much of the math behind it, if we're trying to figure out the formula for the worst case scenario, so the maximum number of comparisons is going to be equal to this 2, the binary log or log base 2 of n plus 2, where n's the number of elements in the array. Okay. So if we're looking at 1,000 items here with sequential, the worst is 1,000. Okay. The average will be 500 or half of that. Okay. With the binary, the worst it can be is the binary log of 1,000 to about 9.97. Okay, so when we multiply that by 2 and add 2 and round up, we get 22. Okay, so the worst this can be is 22. The average for the sequential search is 500. So you see where this becomes a good thing if you can do it. Again, it's not the slam dunk you think it may be because the data has to be sorted. Okay. So one more thing to look at here. Okay. That's not what I want to look at. Let me look at the correct thing. There we go. Okay. And this is something, again, that will hit a lot more, or you will hit a lot more when you take an algorithms class. And it's this idea of the asymptotic notation or big O notation. Okay. You'll see this a lot in computer science. And it's a measure of the efficiency of the program. Okay, we'll see this with the sorts as well, so it's worth going through a little bit. Again, I just popped up the book here, and you certainly can go through this in more detail, but you get the idea as you're going through the time it would take. Here are the basic categories that we see. Okay, if something has a big O of n, it means that no matter or whatever the number of elements that there are has to touch each one twice. If it's 100 element and it's big O of n, it's going to take you 100 times to find the answer. Okay. And you can do that again, the max, the min, or best case, worst case, and average. The log 2 of n is going to be taking the binary log of that number. And you see here some examples of that. You see that's much better. Okay. Some values will have n log n, we'd say. It's all binary log. Okay. Which it's going to give these values here. Could be n squared, which is worse. Could be 2n, could be n cubed, could be uglier than that. Okay. So you can see how these grow, in particular with the exponential, really badly. Like I said, 2 times n, that's 2 to the n. That's exponential. That's the worst case scenario for sure. Okay. So again, this is showing some time. If you're on a computer that executes 1 billion instructions per second, and you see that for something that is at n, or even better at n log n, which is the best you can get, pretty much. Well, there's constant time, but that's something you just know the answer immediately. Is the 0.007, is that microseconds, milliseconds, whatever it is? Not much, okay? Whereas if we're at exponential, it would take a whole bunch of years, okay? Just at the size of 100. So it does become an issue for sure. And this just the graph here, this is figure 18.5. It's going to show the growth rate. And you see the 2 to the n goes straight up. So where you want to be is at this log 2 of n. It's going to be a much more gradual growth. Okay. And that's kind of the idea behind that. Okay. So we'll see that again when we get to the search stuff. Okay. So this is part 1 of this chapter. And again, we talked about searching, binary versus sequential, how to code those up. The next video, we'll talk about sorting, what some of our options are for that.